Welcome to the TWIML AI podcast. I'm your host, Sam Charrington. Hey, what's up everyone? It's been nearly 3 years since we launched the TWIML online meetup, initially as a way for listeners to connect with one another and study academic research papers together. The group really took off in mid-2018 though, when I mentioned offhandedly in my interview with Fast.ai's Rachel Thomas that I'd be taking their course, and I invited the TWIML listener community to join me. That led to the very first TWIML study group, and the folks who came together for that group have become the backbone of a community that's now over 3,000 members strong. Fast forward 18 months, and we've supported each other on our personal learning journeys and a wide variety of courses from Stanford, Fast.ai, DeepLearning.ai, on Kaggle projects, and much more. I say all that to say that I am humbled by the role that we've been able to play in helping folks learn machine learning, and I am excited about the new educational programs that we're bringing to the TWIML community this year. We recently launched a collaboration to bring you the Causal Modeling and Machine Learning course and study group, which I've mentioned here before, and today I'd like to share some new details on the AI Enterprise Workflow study group that we're launching in just a few weeks. If you've been listening for a while, you know that I am very excited about the work going on in the ML and AI communities to make developing and deploying machine learning and deep learning models in the enterprise more accessible and efficient. In fact, we hosted an entire conference, TWIMLcon AI Platforms, on this topic just last fall. Until now, there have been very few formal resources that folks could turn to learn real-world machine learning workflows and deployment strategies. Our folks at IBM are working to change this, though, with the AI Enterprise Workflow specialization that they recently made available on Coursera. And I am super excited to share that we've partnered with them to host a study group for this 6-course specialization program, which I will personally be hosting. The courses in this sequence teach real-world machine learning in an enterprise environment, including applying the scientific process to understanding business use cases and structuring data collection, visualizing and analyzing data, and hypothesis testing, feature engineering and identifying and addressing data biases, selecting the best models for machine learning, vision, and NLP use cases, and using ensembles, deploying models using microservices and containers, Kubernetes, and Apache Spark, and applying unit testing to ML models and monitoring model performance in production. I am really looking forward to working through these courses, and I would love for anyone interested in these topics to join me. If this sounds interesting and you'd like to learn more, I invite you to join a webinar that I'm hosting with Ray Lopez, the course's instructor, on Saturday, February 15th at 9:30 a.m. Pacific Time. To register, visit twimlai.com/AI workflow. And now, on to the show. All right, everyone, I am on the line with Nemo Semret. Nemo is the CTO at Gro Intelligence. Nemo, welcome to the TWIML AI podcast.
Thanks. Happy to be here.
Awesome. Let's jump right in and have you share with us a bit of your background and how you came to work in the intersection of machine learning, AI, and global food security.
Great. Yeah. So I've been at Gro Intelligence for about 4 years now, 4.5 years. And before that, for many years, I was an engineer and tech lead at Google. And obviously working on a lot of things that are technically similar in terms of machine learning and using data and mathematical algorithms. What brought me to Gro Intelligence, well, first I met, it was the founder, Sarah Menker, had a really compelling vision for why this is an important area to be working on today. And what brought me here was that, A, we're solving some really important problems, some of the biggest problems affecting the world. And secondly, I think that the timing of the problems that we're trying to tackle is really appropriate, meaning maybe 10 years ago, this what we're trying to do today would not have been realistic or would not have made sense. And 10 years in the future, it would probably be not so interesting anymore because it hopefully will have been done. So I think we're kind of in a sweet spot for this industry. And then thirdly, I think what makes it technically interesting is that from various perspectives, whether it's computer science, satellite hardware, data storage, and infrastructure, a lot of different enabling technologies are available to us today, and so make this problem not just important and but also feasible. I mean, addressable today.
You mentioned Sarah. I had the opportunity to hear her speak at the Black and AI workshop at last year's NeurIPS conference. And so had a chance to learn a little bit about what Grow is up to. First of all, she seems like an amazing person to work with, but also she does a very good job at articulating the motivation behind what you're doing and the importance of the work you're doing. Can you share a bit of that with us?
Yeah, I guess the one way of putting it is, what we do, forgetting the technical aspects, is basically we help people make better decisions in the world of food and agriculture. So motivations, I think, are that data-driven decision making hasn't quite taken hold in this industry, and obviously it's one of the largest industries in the world. I think about 2 billion people in the world are involved in the whole industry of food and agriculture, from production all the way through to distribution and so on. Um, and this world is, number one, changing pretty rapidly as economies develop and cultures change. People's diets and what type of food they eat change. So people need to make better decisions about what's going on, in the world of food.
Hmm.
So, besides the social and cultural changes, and economic changes, another aspect is obviously global warming has thrown a lot of uncertainty in many different food-related scenarios. And then maybe even more short-term, you have trade wars and tariffs and deforestation and things like that. So
Well,
there are a lot
and
of
locusts, is that
and,
something
and
you're involved in? There's apparently a massive locust swarm currently in Eastern Africa, and it's expected to make its way all the way to India.
yeah, absolutely. This is a huge topic in the last couple of weeks, and that's exactly the type of problem where we would help people make better decisions on. So, if suddenly this infestation shows up, there you would, if you were trying to decide, well, what does it really mean in terms of food supply, or on not just in total, but like how will it affect this region, that region, this type of crop, other types of crops? What will it do to prices, imports, exports? So yeah, connecting all those dots together and trying to make a more informed decisions, regardless of whether you're a supplier or a consumer or a processor, is basically the type of problem we help to solve. But yeah, I think that's a great example. A few months ago, maybe you would have chosen to mention the U.S.-China trade wars as an example, or the swine flu that's affecting um, pigs in Asia, or the forest fires in Brazil and the Amazon. All of those are really great examples of the type of really huge events that affect our users, and that we try to help them deal with.
And so, who are the typical users, and maybe a bit more concretely, what are the specific types of problems that they're trying to solve?
Okay, great. So yeah, I think one thing that is important, there's quite a lot of buzz in this world of agriculture these days, ag tech. So one
Hmm.
distinction that I want to make is, sort of this ecosystem can roughly be split into two categories. There's one that you hear a lot about, which is precision ag. So this is what we don't do. I'll start with that. And so there's a
Hmm.
lot of really cool tech related to helping farmers make very, very local decisions,
Right.
meaning even every square foot of your field, you could say, well, should I put more water here? Should I put more fertilizer there? And so you would have instruments and measurements on the field level, and down to subfield level decision making.
An example here might be like Blue River, which was acquired by John Deere. And they had a technology that you'd put on the back of a vehicle that would they would identify weeds and spray fertilizer on the weeds to make them burn out or something like that.
Exactly. So it's so the different, but then so that's what we call precision ag, or what the world in general calls precision ags. It's
Yep.
really advising things maybe on a few feet at a time. We're dealing with a different class of problems, which we don't think there are any great solutions for right now. But it's more macro. So maybe you're not trying to decide what to do on every square foot, but if you have a chunk of land and you're trying to decide what is the best use of this land, or then in terms of what types of crops are suitable in this place, what other parts of the world have had success with this type of crop, what are the environmental conditions that make one type of crop versus another. So basically, one example is, what should I do with this land in 6 months, 1 year? Another example is, well, if you've been producing a certain type of crop and you're concerned about the trends in production of that crop in other parts of the world. Let's say you're a coffee producer from Vietnam, which is a very large coffee producer, and you're worried about oversupply or shortages. Well, you should be able to quickly analyze what's going on in Brazil, even though you're in Vietnam, because you're essentially working on the same commodity. So that type of decision, you'll say, well, will the production this year be greater than expected, less than expected? What's the weather like in the different producing countries? What are the expected yields? So those types of decisions in terms of what crops to plant, how much to expect in terms of supply and demand are another category. And then going on down the line, you could be, let's say, a food processor, and you're buying, wholesale wheat, let's say, or corn, and you want to know where to buy it from, and maybe you're importing it from different places, so you want to predict which countries or which parts of the world will have shortages or excess supply. That's another example. Or continuing in other domains, you could have a financial application where you're, let's say, lending money to farmers. So if you want to know the probability that these loans will become delinquent, and that means you need to understand the environment and what the climate is doing to the farmers, and the probability that their crops will fail, for example, or that there will be a drought, or things like that, or that on the contrary, that there will be a huge production and then the prices will be low. So all these things obviously affect the livelihood of the farmer, and therefore, as a lender, you would want to know the probability of those things, whether you're, or even if you're providing insurance, crop insurance, and you could be a bank, you could be a government, you could be all kinds of different entities that deal with that. And there's a long list. And another macro type of decision that we enable is, impacts of diseases. That I mentioned swine flu. This was a big topic in the world of agriculture last year. There's aflatoxins. There's like all kinds of different pests and diseases and things that affect crops that are affected by weather and climate. So, or the locust that you mentioned is also, it's a cyclical phenomenon, but the intensity depends on weather. So if you wanted to know that it was going to be more severe or less severe than usual, those are the types of decisions that we would help you make.
And now you started with talking about kind of macro level land use and how that's different from the precision ag. Is the implication in part that you're less worried about the actual land itself? Like it's clear that a big part of what you do is like market analytics, if you will, and like the entire like supply chain of agriculture and different forces at play there. But are you also looking at the nutrients in a kind of macro plot of land, or is that all left to like the precision ag piece?
No, that's really important, actually. Yeah, even so, for example, let's say you're trying to understand if there's a shortage of one crop, how much will people substitute? How much substitution would there be in another crop, right? And a big part of that equation is understanding the content of it. So, for example, we don't just try to predict the how much wheat will be produced, but we try to predict how much certain types of wheat would be produced, because they have different protein content, and that affects a lot of things, everything from how much will be consumed for different uses, and as well as what the prices will be for different categories of things. So yeah, protein content or calorie content of different crops is a huge part of it. Also things like, if what's the trade-off between, I'll give you an example. I mentioned the swine flu. So that's a disease that's been affecting the pigs in China, and it's a huge deal because that's the main type of meat that's consumed there. Well, you might want to know, well, okay, if there's suddenly a shortage of pork, would that translate into an increase in chicken demand, right? Because people, if pork becomes very expensive, maybe people will start eating more chicken. Now, there's obviously many variables there, culture and so on. But one of the key components is, well, how much nutrition do you get? Like, what's the equivalent amount in terms of grams of protein between these two things? The biology of plants and understanding the content is critical, even at the macro level.
Now, when I think about all of the problems that you just described, and then think about data that I might want to have access to in order to begin to try to solve these problems or, provide some insights about them,
Mm-hmm.
that seems huge. Almost, I don't want to be hyperbolic, but like infinite. Like there's so much data that you could plug into or might want to plug into, a system that solves these kind of problems. Like,
Yeah.
what are your typical data sources? How do you approach data acquisition?
That's a great question. So I think that, just to cover the types of data. So the first thing people think of, and that jumps to mind because it's visually important and quantity wise it's important, is satellite data. We have, in
Mhm.
terms of just sheer volume of data, that's the majority of our data. Obviously, we have incredible amounts of information about every pixel on Earth, and it's not just images in terms of the visual photography that most people would imagine when you think of a satellite picture. Some of it is infrared and ultraviolet, and so different. All the entire frequency range of the electromagnetic spectrum has information about what's going on. So what happens is that you have different satellite hardware which is able to capture different bands of this electromagnetic signals bouncing off the Earth, and from that some of it is visible, and some of it is not visible, but from that you can derive really complicated and very useful things. For example, obviously you can derive temperature, which, well, maybe it's not so obvious. Like, how can a satellite that's way up in orbit know what's the temperature on the ground? Well, it looks at various signals bouncing off the Earth, and there's a well-established science that says, okay, but we fit a mathematical model around that, and we can determine based on the electromagnetic signature what is the temperature on each point on Earth. Similar to how you can look at a planet or a star and figure out its chemical composition just by looking at the electromagnetic signals that come out of it. We can do the same thing with the Earth. So it's temperature, rainfall, including microwave signals, so you can get an idea of what kind of clouds there are, how much rain is there, and how much humidity is coming out of the ground, and so on. So you can estimate temperature, rainfall, or more complicated things like evapotranspiration, which is an extremely important signal. It tells us how much, as the name implies, how much water is being released into the atmosphere from the transpiration or like sweating of plants. And that's a really important indicator of plant health. And similarly, there's another signal called vegetation index. So again, looking at just the colors and the infrared signals, the red and green and infrared, you can determine how much biomass there is, like how much living matter there is in the flesh of these plants. That's also an extremely important signal. And you can get this information from satellites at an individual pixel level and covering almost the entire world. So there's enormous amounts of data that's from satellites, and that's rapidly changing. and probably the biggest part in terms of volume. Not probably, it's way more than half of our data. But in terms of importance, and this is a key point for us, is that, well, it's the economic data and social data is all equally important. So prices, for example, or commodity prices, or retail prices, or production quantity, or yields, historical yields, or how much fertilizer has been used in one place or another. What is the cost of transportation from one place to another? All of these things fit together to enable people to answer these complex questions that typically involve climate, weather, economics, and society.
Even within economic and social, you've got kind of wildly disparate data types. You've got, I'm imagining, time series data that you need to deal with, as well as, documents that are best considered from an NLP type of perspective.
I mean, one of the challenges is, so just as a baseline, many countries, governments, and non-governmental organizations and companies have been collecting enormous amounts of just basic agricultural data, in some cases for a really long time. Like the US Department of Agriculture, for example, has over 150 years of data on everything from the yields of every single crop in every single county in the United States to the production and how much area was planted, and the crop conditions, meaning were they healthy, unhealthy, what percentage of the corn in in this particular county was considered good as of July 3rd of this year, for every year going back. So there's incredibly granular data that we're tapping into. And same thing, from the United Nations, from the World Bank, from all kinds of different organizations, academia. So besides the obvious satellite data, there's enormously amounts of ground-based data that have been collected. And yeah, as you mentioned, some of it is really organized nicely and has modern APIs. Let's say for exchange rates, we have excellent APIs, and we're not reinventing the wheel. You can get currency exchange rates in a really good way. But in some cases, it's obscure data sets that were typed up, 75 years ago, and now exist as some text that's been scanned into an image, and then the image has been put into a PDF, and maybe it's in a different language. So, so you would do a combination of OCR, optical character recognition to extract the text from the images, and then do NLP to interpret that text, and then extract structured data at the end of the day from that, which could be like yields, for example. So the data itself is often a big part of the challenge.
We probably could spend a whole hour talking about the data, but let's maybe take a step back and kind of contextualize this by looking at the types of problems you solve. So we've talked about this from an end user perspective, but do you approach each of the problems that your customers are looking to solve as kind of one-offs? Like, do you do consulting, or do you have specific categories of products that you offer, and most of the work you do kind of falls into different types?
Yeah, no, great question. So the first point, I think, is that we're offering a platform. So everything we do, as much as possible, except for obvious some rare exceptions, everything we do, we attempt to really productize it and make it scalable and make it available to all our users. And we're going to talk a lot about machine learning and AI, but I think one important point is that we offer a platform where people can access all of this data in a highly organized way, and then they can access it visually through a web application or through an API. And we expect our customers to also build their models. So in a way, we're providing sort of this platform that gives you access to enormous wealth of data, creating value by deriving data on top of these existing data sets, but also making you able to access it in a really organized way. So one of the applications that we have for AI is we've structured this information into a knowledge graph. So we have, or what some people call an ontology. So we have the Gro ontology, which organizes, data from hundreds and hundreds of different sources into a common language. So if we're talking about wheat, and there's many dozens of varieties of wheat, that a bit of data from one source that tells you maybe the protein content of wheat, and then another source that tells you the price of wheat. Well, we have to make sure that the specific type of wheat that these two things are talking about is the same item. So organizing all of that information into a structured knowledge base, or in the form of a knowledge graph that relates all of these entities, is a key part. And then our users can use that through an API or a web app to find insights in the data. And in some cases, we will do the extra work for them in terms of like building forecasting models, predicting things that the world is interested in, and making that part of the platform as well.
And so for the different types of modeling tasks and the machine learning applications, what are the types of problems that you're typically attacking?
So roughly, I think there's 4 classes of problems. One that the first one is yields, agricultural yields, which is a hugely important. We've been now doing that for about live in production for a little over 3 years. So this is things like, for the first example was, can you predict the yield of corn in the US intra-year? So meaning we're now, in February 2020, we already have a prediction of what the final yield of the US corn production will be, meaning how many bushels or how many tons of corn will be produced per acre on average across the United States, as well as down to every single county. Now, we're in February, so nothing has been planted yet. So we have a model that's based on historical trends, but as the season progresses, and we get into March and April, and things are getting planted, and they're starting to grow, and we see the weather, our prediction gets constantly refined. So when we say yield models, basically telling you the conclusion that we will reach a year from now, meaning how good was the corn yield in the US in 2020, we're constantly estimating that through a yield model. So if you log into our product every day, whatever little bit of information comes from the world that would help us better forecast the US corn yield will be incorporated, and this is fully productized, so that there's an answer updating itself every day. So why this is interesting, obviously people have been concerned with US corn yields for a really long time, but traditionally it's been done through very slow processes where there's a lot of human and subjective elements, and maybe you'll have official updates on this year's forecast will be updated maybe once a month throughout the course of the year. So we're saying that we'll make that completely objective, automate it, and do it every day. So we did that for corn in the US and started outputting our predictions in real time. And it proved to be enormously successful in 2017, 18, 19. In those seasons, we correctly anticipated the final result in several instances before the market or any other forecast or the traditional forecast had detected them. And when the truth finally came out, in terms of when at the end of the season, when the full crop was realized, each time we'd sort of been out on a limb and predicting something unusual, it turns out we were right and ahead of the curve. So that was an enormous success. So that's yields. And then we've done that now 10 times. We did it for corn in the US, soybeans in the US, in Argentina, and in Brazil, wheat in India, in Russia and Ukraine, and corn in China as well. So again, a number of different cases where we've managed to build really good yield models that are sort of the state of the art, and have been able to predict real world events before anybody else was. So that's been one area of huge success, yields. And in each case, like I said, we don't. Our customers would also they'll look at bananas in Ecuador tomorrow, and we may not have already built a model for that particular case, but we've shown a general framework that applies to many crops across the whole world. And more importantly, we're providing you all of the data so that you can use our models and use our outputs, or you can also use the data and produce predictions of your own if it happens to be a series that we are not explicitly forecasting. So that's yield. And well, before I move on to the second area, one thing I wanted to say is we're very strategic about what we choose to model. So for example, in the yield case, I gave you a bunch of examples. Each one sort of pushes the envelope in a new, interesting way. So, for example, compared to the US, let's say one of the key pieces when we started modeling wheat in India as well. A big difference is in the US, most of the heartland, the corn belt or the wheat belt and so on, especially corn, is concentrated in the Midwest. So even though it's a huge area, the climate in the major producing areas doesn't change that much. But then you go to India and you say, okay, India produces a lot of wheat, but it's planted all over the country from the north to the south. So that it's actually a key technical challenge that this new example introduced is that, well, how do you do accurate crop masks? How do you model the effect, when it's a wide range of latitudes from north to south and the climate is very different. And then the second piece there is, unlike the US, the farms tend to be really small. So figuring out, which points have wheat versus rice versus corn and so on, and or just forests and other things is much more difficult in India. So just all that to say that each of these examples is sort of pushes the technical envelope in a different way. And so and so yield is that's one big area where we've done a lot of work. And if you go to our website, we've published a bunch of papers on that. And in our products, where, as I said, these forecasts are there on a daily basis, fully automated. A second area, fairly closely related, is crop masking. So that is a key piece of yields, but it's yield forecasting, but it's its own problem. It's basically looking at satellite imagery, as I described before, not just visible, but the whole spectrum. Across time, we try to predict what is, or to figure out what is going on in each pixel in terms of, is there wheat being planted? Is there sugar? Is it bananas? Is it coffee? Is it what the crop is? And this is extremely important. And we do that by looking, and that's called crop masking. So it's an important point because by itself, it's a really useful bit of information to have.
You're essentially trying to label each pixel with a crop.
Yeah, and most of and what makes it complicated is that, well, first of all, a lot of crops look the same in terms of, so you use things of how they evolve over time. If it peaks in, if a certain signal peaks in July versus it peaks in August, then it tells you whether it's this crop or that plant, this other crop. But yeah, so we're trying to figure, and then secondly is that if you could assume it's all constant, then it's a fairly well solved problem. You can, but the problem is, the world is dynamic. So even in the same farm, there's a thing called crop rotation, where people, for various reasons, will plant different things every year, and sometimes it will be a predictable cycle, or sometimes it's driven by the weather, and sometimes it's driven by market conditions. So that happens a lot in the US with corn and soy, for example. The same farmer could choose to use this land for corn or use it for soybeans. So if you're trying to predict the corn yield of this year, 2020, knowing which pixels are corn and which pixels are soybeans obviously has a huge impact, because when you then apply the other signals, let's say the temperature, you need to know, am I looking at the temperature in a spot where there's corn, or am I looking at the temperature in a spot where there is soybeans, because it will have a different effect. So crop masking is its own problem, even though it's an important input to yield. It's its own huge problem, and so that's a big area where we're doing a lot of work in, and that's a different type of machine learning. So yields that I mentioned before is you often using regression methods, whereas crop masking is heavy on image processing, and in-season crop masking is a combination of these image cubes over the same place over time. You apply with neural network techniques applied to it, help you make a much better guess than otherwise in terms of what each pixel is. So crop masking is another example, and that one uses a lot of image processing. A third example of class of problems we work on is droughts. That's very similar to yields, but for different applications. But predicting droughts, there are standard international classifications of, and these are discrete classifications. This is a drought of level 1 or level 2 or level 3, and these are correspond to severities, kind of like you have hurricane severities and so on. So unfortunately, the world doesn't have a single automated, fully objective way to classify the entire world and say, okay, is there a drought? Yes or no? How intense is it? Is it a 1, 2, 3, 4, 5, or 0, or meaning it's totally normal? So what we're trying to do, but there is some manual processes that have been developed over time, historically. For example, governments like the U.S. government will pay, or many governments will pay farmers if there is a drought. It's a drought insurance. So that type of stuff, is very inefficient because there isn't a single benchmark. So we're trying to create a completely objective drought index that the entire world can agree on. And it applies for the every place in the world, takes into account all the weather and environmental signals, and produces a consistent labeling, of drought severity. And so that's an interesting class of problems that we're working on. And the fourth category that I haven't mentioned yet is a completely different type of problem, which is the knowledge graph automation. So as I mentioned, we bring in data from dozens and dozens of sources all the time, and we want to organize that into a common ontology, so that if we have some data, like I mentioned, about corn, we know it's about corn. If it's yellow corn, we know it's about yellow corn, etc. Or we know if it's temperature on the ground versus temperature, on the ground land surface versus temperature, in a weather station a couple of meters above ground. It's a totally different concept, like the temperature of the ground and the temperature of the air. So our system has to know what exactly you mean by temperature. So this means it's highly, highly structured. And that means all these data that come from outside sources have to be mapped and transformed into this common structure, so that we're referring to the same entities. And that, as we're growing exponentially. We currently have about 55 million data series, a little over that, in our platform, and it's doubling every 6 to 9 months. So one of the key pieces is that we want to be really accurate, but also efficient about mapping outside knowledge into our internal knowledge graph. So that means we have a whole class of problems related to knowledge graph automation. So that involves graph algorithms and NLP, and slightly less structured, so neural network approaches and so on, that will help us. You say when we have a source that says, if and some of it is just plain language translation as well, but it's really understanding that, hey, if we have a Vietnamese data series that talks about the yields of rice, and there's 3 varieties of rice, it's really important that we map that correctly into the items that we call these 3 or 10 varieties of rice, and making sure that the Vietnamese word and the English word are referring to the same thing.
Right. So in addition to any models that you're using to kind of extract the data, for example, you talked about pulling tabular data from PDFs. You're also using models to kind of dynamically update the way data is kind of ingested into this knowledge graph and how it's labeled and things like that.
Exactly. So the knowledge graph, you can think of it as knowledge graph is sort of the foundation, and then using that knowledge graph, we map stuff. And we automatically try to learn what the description of things that come from outside and map that into our ontology. So that, but this part, by the way, I think is an important thing to note is AI will help us get 80-90% of the way there, but we still have human beings really review and understand these things, so that if our knowledge graph automation says that, maize is the same thing as corn, well, there's still going to be, unless it's like 99.999% confidence, there'll still be a human who says, is maize really the same thing as corn? Yes, it makes sense, and proves that. So,
well, it's a lot easier to fix those problems before you pollute the pool, so to speak, when you have, what did you say, 55 million data series that you're managing?
Yeah, exactly. So I think the sometimes the way the data comes in from outside, sometimes it's not clear not every source has a cleanly organized way of representing what something is versus how it's measured, and things like that. So that's we're creating the transformation instruction set, if you will, through AI.
Speaking about kind of that quality of that data set that you're working with, how do you try to account for noise or missing values in the data that you collect? Do you kind of have a principle that says we're just going to record what we're given, or do you try to correct it on ingest? What's your approach there?
Yeah, no, great question. So I think for us, reproducibility and attribution is really, really important. So at the bottom layer, or I should say the first layer in our platform after the data has been transformed, the values that we have can be directly traced to where it came from. Right? So if we say, the NDVI of meaning the amount of vegetation in this particular pixel is 0.5 or whatever, like then we'll have that value where it came from. If the source revised it, we'll also annotate that and say, okay, this was yesterday they said it was this much, and then today they revised it to this much. And this applies to economic data as well as satellite data, hardware changes or algorithm changes. So even after transformation, we always have the original value, and we annotate it with things like when it was reported, when it was revised, etc. So all our data series are actually three-dimensional in the sense that there's the value, there's the time, and then there's also the potential revisions that could have occurred in the past on that particular point. And that's really, really important, especially when you're dealing with things like estimates or forecasts and so on. And then, and of course, it's very important because we don't know in advance every single use case that people will be using it. So if you've done some analysis and then the data changes because the source made some corrections, it's really important that you can, as a user, you can totally see why that happened and where it came from. That said, on top of that, we do a bunch of things. One is that, as I mentioned, we build models. So we create brand new data that are forecasts and predictions and so on from the existing data, and those are available in the data in the platform, just like other things. So as I mentioned, the yield and the drought index and all these things that I mentioned. We also do a lot of Gro derived, which is Gro derived data series, which are like basic operations that combine data from multiple sources. So, so for example, you may have trivial example would be we have population data from, let's say, the World Bank about every country in the world and how it's growing, and including projecting it into the future. And then you have consumption data, let's say, from some other organization. Well, then, and well, if you join those two, you can get per capita consumption, which, so you get some data from one source, some data from another source, you combine them, and you create a new data series that's of independent interest. So that's so we do a lot of those types of things as well. And then finally, I think the most basic answer to your question, though, is that we try, if something is fundamentally difficult data, we often try to get multiple sources. So if you go into our product and you say, how much sugar was produced in Brazil last year, or even last month, there's probably 5 different sources that will tell you that we have, that give you that number, and they might differ by a few percent because they use different methodologies and so on, and you can take them each individually, or we could give you the average of them, or we can give you what we've selected as sort of the best combination of things. So yeah, the answer is often you triangulate the truth from multiple sources. And that's often a big part of the value, right? If you look at especially these hugely economically important commodities, there's a lot of speculation and hidden information and so on. So a lot of the use cases are about getting the same information from multiple sources to get a better version of the truth, and then building decisions on top of that.
And with that, the speculation and competition, even on kind of nation state stage, do you worry about adversarial use cases or data poisoning or anything like that?
Yeah, I mean, I think, we don't have any specific concerns, but it is the type of thing that each customer would have their own concerns. So we try to make sure that if there are multiple versions of the truth, we try to get all of them, or all the relevant ones. At the end, so I think, but at the end of the day, also satellites are, it's hard to lie to a satellite. Although it's possible, you'd be amazed at the adversarial things that can be done. But yeah, I think there's no magic answer. It's trying to get the best possible information, the most objective possible sources, and then make sure that it's interpreted and mapped and organized correctly. And then obviously, then when we do modeling, we spend an enormous amount of time back testing, looking at historical data, looking at different algorithms, and I think this touches on another point which is really important that we haven't discussed yet, is that we try to avoid black box models. If it's possible to predict something or forecast something with a model that has more explanatory power, a slightly transparent model, we will versus a black box model, we will prefer the former, all else being equal. So, for example, we talked a lot about yield. If we say, well, we think the yield is going to be higher than expected this year, all of a sudden, then we want to be able to say, well, the reason why our forecast is optimistic or whatever, or just changed yesterday relative to today, is because this signal moved, right? And that's a hugely important thing in terms of building confidence in the models, and also letting people use them in the real world. So if you have a model that says, for example, the yield of soybeans in the US was dramatically affected by the temperature in November, then that doesn't make sense, like physically, because by November all the soybeans have finished growing and they should be harvested by that point. So that's why would the temperature affect it physically, biologically? So our models kind of are not just black boxes where you just throw tons of data and see what comes out. It's really saying, like, well, we want the model to model reality and understand the signals that go in are signals that make sense from a process physical point of view. And then we can also open the box and see what it's doing and understand it, and it makes sense from a biological and economic point of view.
It certainly makes sense that all things being equal, you'd prefer the more explainable things, but often all things aren't equal. Do you find that you have specific use cases where the advantages, performance or otherwise, lead you to use black box models?
Yeah, so I think yes, and then it's a trade-off. But again, we're not. We'll do whatever is the best trade-off. So there are cases where it's a little bit black boxy and a neural networky, but and like I mentioned, for example, the image processing and crop masking over time. It could, it could be, if it's, sometimes you would be able to explain it, because let's say, like I mentioned, there's rotation between crops. Sometimes it's a very regular thing. Let's say 1 year you plant soy, 1 year you plant corn, and you either. And so, if it's a very predictable pattern and that comes out of it, then you're like, oh, okay, that pattern was picked up. But if it's a much more, but sometimes in this case, this is an example of, we've tried both approaches, and there are cases where, I shouldn't say both classes of approaches. And there are some cases where, so we reached the limit. So we went through the classical approach where it's not black box, and we're explicitly modeling every single signal and looking at its temporal signature and saying, when did it turn on, when did it turn off, and trying to fit it into very specific models of behavior. So we've done we've gotten really great results, but sort of we got to the point where we want to go even further and get higher accuracy. And in that case, you have to take models with many thousands of or tens of thousands of signals. So you're not necessarily going to be able to interpret it every time.
And do your models tend to be, wide or monolithic types of models, or do you rely heavily on hierarchy and ensembling and things like that?
More of the latter. So, for example, when we forecast, hierarchy, timescale hierarchies are really important, because the nature of let's go back to the yield example. If you look at and yield, by the way, is super important, because that's the hard variable. Ultimately you care about how much food will be produced, but the amount produced is yield multiplied by area, right? So the area is relatively easy to estimate. Again, there's parts of the world where that's hard too, but so the yield is the sort of the magic variable that everybody is paying attention to a lot, because that's the one that changes year to year, if it's too cold, too hot, etc. So yields, but are driven by two very different timescales. One is, if you look at the yield over 100 years, you'll see just dramatic improvements. And depending on the crop, that curve will look like an exponential or a straight line or a sigmoid shape. It's kind of like how you have Moore's law in electronics. There's similar things happening in crops, because people get better at breeding the right seeds and figuring out what seeds work where, and things like irrigation comes in, or pesticides or fertilizers. So there's just long-term trends that are very important. So that's the long-term trend model, and that's one time scale. But that will only give you that won't tell you what changed unexpectedly in 2020 or in 2019. So we do construct yield models explicitly as two levels. One is a long-term trend model that's saying, even on the first day of the year, before a single seed has been planted, we already have an idea of where long-term progress should be. And it's different for every country and every crop. And then off of that baseline, so that by itself is valuable, right? Like, you could just have long-term forecasts. I can say, okay, this is what it's going to be like, in Germany in 2021, and in India or Pakistan in 2022, etc. You can have forecasts. But then the intra-year part is saying, okay, what's going on this year? How much has been planted? What was the temperature at the time? at different points
Right.
season and so on. So the in-season model is taking a whole bunch of other daily and weekly and so on signals, whereas the long-term model is taking annual and historical trends. So yeah, yield is an example where decoupling those two, and you could try to model just just model it as a time series without doing that, but then you're just the problem becomes way noisier and harder, and you just don't get good results. So it's very much So that's one example. Another example is demand on the demand side, which we haven't talked too much about. But if you are trying to forecast consumption of different things, similarly, again, there's some long-term trends that are driven by like economics, and culture. So, for example, the many countries throughout the world, as the GDP, as the income per capita increases, and people rise out of poverty, the amount of meat that they eat is going to increase, because when very poor people generally can't afford to eat meat of any kind. So as countries develop, one of the things you see is the diets start to change. So those types of things are macro long-term trends. So you definitely need a long-term model for that. But then on top of that, on any given year, prices could be high, and so the demand for one thing could be high or low, or things, trends can change. So similarly, on the demand side, there's also these short and long-term timescales, and modeling them explicitly makes the problem much more solvable. And I think more generally, if we're trying to, we feature engineering and hierarchical modeling is really important. Again, it goes back to the point about black boxes. We have, as I mentioned, 55 or 56 million data series. And if you translate that into different values, it's in the hundreds of trillions of data points. So one approach would be, hey, for every problem we have, just throw every data point in that exists in our platform into it and see sure, let the machine learn it, right? But the problem is you can't give a machine like 600 trillion data points and say, okay, predict one value. It needs a lot of help. So we have enormous amounts of expertise in the company in terms of remote sensing experts, agronomists, hydrologists, and people like that who are saying, okay, well, don't just throw a million features. These are the 100 features that really should matter, right? And then when we see impact of different features, we can say, yes, that makes sense that this phenomenon this cause has this effect, because we understand how these, whether it's biology or economics or transportation or what have you, there is some domain knowledge that says, yes, this makes sense.
Well, I know we're running a bit long here. If you've got time for one more question, I'd be curious to have you, just give us a sense for your overall modeling process, and in particular, if there are any unique aspects to the way you approach models beyond the things that we've talked about thus far systematically.
I guess the one of the key things is what we choose to model. As I mentioned, we have a platform where you could really be modeling a million different things every day, because we're giving this highly organized platform that allows you to answer all kinds of questions. There's a few things we do before we decide to model something. One is it an important problem to model, right? Like all the examples that I gave, they're not just they're economically really interesting for our user base. So and like for example, I mentioned a couple of times wheat in India. Well, there's really cool scientific and technical challenges, but the first question is, does anybody care? And in that case, the answer is yes. It's a huge question, because historically, India obviously is one of the largest countries in the world. In terms of population, and the second largest, and but historically, and wheat is a big staple there, for the people of India, and historically, though, for the last 50 years, India has been self-sufficient mostly. So they produce a lot of wheat and they consume a lot of wheat, but it doesn't quite interact too much with the rest of the world's wheat. But now, because India just continues to develop economically, and as well as there are some theories that their green revolution of the last 50 years is sort of leveling off, and they've kind of some people are concerned that their production will not continue to rise as it has, but the demand will continue to rise. So if that happens, and suddenly a small percentage change in supply and demand of wheat in India could translate into enormous amounts of imports, right? Because it's sort of like, you have this huge number of production and a huge number of consumption that are kind of well balanced. But if there's a small change, even a 5 or 10% difference shortage, and then they need to import that much, then that means, a huge new source of demand in the world, and maybe Australians will start producing a lot more wheat to export to India or Canada, and other countries who are importing will have to import from other places. So it's sort of like this big iceberg that's hiding under the water that could have a big impact. So all that to say is that the first part of modeling process is it an interesting thing to model from a business point of view, and is it fundamentally, and so but that and there's a lot of them, but it's important that we work on the right ones. And secondly is then we like I said, we don't come at a problem with a solution, which I think distinguishes us from many companies where we didn't start out as an AI company saying, well, let's just find a problem to work on and stumble into agriculture. It was more a joint thing of figuring out that this particular domain needs these answers and needs better decisions, but we don't care if we end up using neural networks or gradient descent algorithm, XGBoost, or random forest algorithms and so on. So we're agnostic to technology, but we want to solve the problem. So I think that the second part of our approach is where every single new problem we're prepared to use different approaches. But third piece is that when we build a particular model, we do try to build a framework that helps us experiment and reuse things in different situations. And so, for example, even though each country and crop is different for our yield modeling, we do have a basic framework that applies across the board. And the input signals will change, but there's 2 or 3 key algorithms that we will always use, and then the specific inputs will be different. But the back testing and how we evaluate our results and so on will be following that process. We try to look at finally when we're getting close to having something that we like and that we're ready to launch, we look at performance in very unique ways. So, for example, we don't look at just the average value of our error or just the single, but even when we're predicting a single number, let's say the wheat yield of Russia, or the Black Sea region, it might be a single number at the end, but underneath it, we're actually making that same prediction in a much more granular way. So we look at, how is the error distributed spatially? Does that make sense? How is the error distributed in the backtesting? Like, what are when we run it, when we backtest historically, does it, what are the years where our model would have performed better or worse, and why is that? And does that, is it just random noise, or is it like, does it give us features that we should model? So we have a very iterative process where we look at spatial, temporal distribution of performance, and bring in a lot of domain expertise to sort of figure out the feature engineering and tweaks that we need to do to have a good model.
Is it hard in your case to know when to stop, when it's good enough?
No, I think we're lucky because, again, from the first point I started with, we usually have a very clear idea of why this is interesting. And together with that comes an idea of what's reasonable to move the needle, right? So in terms of to add value to the world. So, like, let's say if you're trying to model something in the United States, then there's typically going to be a lot of really good inputs, a lot of historical data, and better than most other places in the world. So our expectation will be like, well, okay, to make a difference in this case, we really got to make sure that our error is less than 0.5%, right? Because anybody can get to within 2% or whatever, right? Like
the data is so good,
yeah, exactly. And conversely, you go to a country or a part of the world where there's very little data and there's or maybe no ground truth at all, so on, and then you're like, well, okay, everybody's the best anybody in the world can do is 10%, so or 20%, or maybe 50% because they have absolutely no idea what's going on. And then in that case, we're like, well, okay, can we consistently, robustly make a forecast that has an error of 10%? And that's awesome. That would be terrible for something that everybody else has a 1% error on. But if everybody else has a 20% error, then we'll put it, and we'll be confident that we're adding value. So we always know when we are adding value and when we're not adding value. And so that gives us an easy way to say, okay, let's launch this. Even though there's a million things that we could do to improve, we're already ahead of we're adding value.
Well, Nemo, thanks so much for being so generous with your time and sharing with us what you're up to there at Gro. Very much appreciated.
Yeah, thanks, Sam. And I enjoyed it. I hope it was informative and inspiring.
Absolutely. Thanks so much.
Thank you.
All right, everyone, that's our show for today. For more information about today's guest or any of the topics mentioned in the interview, visit twimlai.com/shows. To learn more about the IBM AI Enterprise Workflow Study Group I'll be leading, visit twimlai.com/AI workflow. Of course, if you like what you hear on the podcast, please subscribe, rate, and review the show on your favorite podcatcher. Thanks so much for listening, and catch you next time.